Hello, welcome back. In today's lesson, we're going to find the horizontal asymptotes, vertical asymptotes, and oblique asymptotes of our rational functions. Okay, so to find our vertical asymptotes, the very first thing you need to write down and remember is that to find these, they need to be in simplest form. So your rational functions need to be in simplest form before we can look for them. Now, so let's go in order. For A, I have r of x is equal to x over x squared minus 4. You might be tempted, because I've seen this so many times, to go ahead and simplify the x and the x squared. You cannot do that. Remember that our division symbol puts everything here in a group. They're all together. So there's actually nothing for me to simplify here. A is already in simplest form. Okay, so now we look for what's happening in our denominator. Okay, we've done this before. I need to see when this denominator is going to be equal to 0, because that will let me know where the vertical asymptote is. So here I notice that it's a difference of squares, so I can use that. Remember, I'm trying to see where x squared minus 4 is equal to 0. So using the difference of squares, I have x minus 2 and x plus 2 is equal to 0. So I can do my split here. Either this is equal to 0 or this is equal to 0. So let me do that. X minus 2 is equal to 0, or x plus 2 is equal to 0. I know I kind of ran out of space, but I'll keep going here. So by adding 2 to both sides on my left one, I get x is equal to 2 and x is equal to negative 2. So this lets me know that the vertical asymptote for A, there's actually 2 of them. There's one at 2 and one at negative 2. Now let's look at B. Here for g of x, I'm looking, and once again I try to see if I can simplify any of this. I can't, therefore it's already in simplest form. I can go ahead and only worry about my denominator. In this case, I only have one thing to worry about. X minus 1, when is that equal to 0? Adding 1 to both sides gives me when it's positive 1, where x is positive 1. So in this case, you only have one vertical asymptote. Where is it? When x is equal to 1. So we found that one. Here, be careful. Don't start dividing here. Remember, this is a whole group. Can I do anything with a sum of squares? No, I can't. I can't do anything else here. So this is already in simplest form. And when I try to solve for my denominator where it's equal to 0, look what happens here. X squared plus 1. When is it equal to 0? If I subtract 1 on both sides, I get x squared equals negative 1. But I can't take the square root here, because if I do, okay, you're going to get a complex number, which takes it outside the real number system. So this has no real numbers where this will be equal to 0. So C actually has no vertical asymptotes. Okay, so far we found 2, we found 1, we found none. Let's look at what happens here. When I look at this, there's a lot of things happening here for D. So I'm going to go ahead and factor this just to double check that it's in what? In simplest form. So I see a difference of squares, so I know that my numerator is x plus 3, x minus 3. And here, if I factor this, I should get 7 and 3 work, and it'll be plus minus. So look what happens. I have a factor here of x minus 3, and I also have a factor here of x minus 3. Now, that lets me know that this is not going to be part of my vertical asymptote. The only one that I'm going to work with is x plus 7. I want to see when x plus 7 will be equal to 0. So if I do that, when is x plus 7, when is it equal to 0? Well, subtracting 7 on both sides gives me x is equal to negative 7. So I don't have to worry about this one, because in its simplest form, this is canceled out. This means something else, okay? This actually means that there's a hole here when I make a graph. So in this case, only one vertical asymptote. And what's the most important thing? That you don't forget to put it in simplest form to look for these. All right, looks like it's your turn. So go ahead and try these 3 problems out. Okay, go ahead and pause the video and I'll show you the answers in 3, 2, 1. Okay, so here are your answers, but let's break it down. So for number 1, there's nothing for me to do. This is the simplest as it's going to get. So I mess with my denominator to see when that would be equal to 0, and I get that my vertical asymptote is at x equal negative 4. Now for number 2, as crazy as it looked, well, let's see what happened here. So my numerator, I factored it out. My denominator, there's actually nothing I can do to it. It's already in its simplest form, so I can't mess with it. So with the denominator, when I want to see when a quadratic is equal to 0, just for me to not keep working in case I don't have to, most of the time I'll start off by checking its determinant. So I put in b squared minus 4ac. That will let me know how many solutions it has, right? When I want to set that equal to 0. So I notice that I get a negative number, which is less than 0. So that means that there are no real solutions. That means that this will not be equal to 0. If I were to graph this, you would see that it does not cross the x-axis, so my y's never become 0. Therefore, number 2 has no vertical asymptotes. Now, what about number 3? In number 3, what I did is I broke it down into simplest form, and I kind of ran out of space. Don't make fun of me. But so I wrote it like this. I would normally never write it like this. I would write it horizontally. But let's see what happens. So my x to the third stays x to the third, but my denominator, I have a difference of squares, so breaks it down like this. And I have, you could have stopped here and just solved this for 0. And you will get the same answer, but just in case I broke it down once more. I can't do anything else to x squared plus 1, because if I try to solve that, I get a complex solution. So, but this one I can keep going with. So I broke this into x minus 1 and x plus 1, and when I solve for those equal to 0, I get that I have 2 vertical asymptotes, at positive 1 and at negative 1. All right, now what about your horizontal asymptotes? There's actually 3 different things that we have to look at. So we need to look at if our rational function is proper. So in that case, if the degree of the numerator is less than the degree of the denominator, then we can break it down further, right? For the rational functions, to see if they're improper, we need to see if the degree of the numerator is equal to the degree of the denominator, or if the degree of the numerator is greater than the degree of the denominator. And here, we'll need to pay some special attention to this one, because here we're going to work a lot. Okay, so let's go on. Okay, so let's investigate our first scenario where we have a proper rational function. So first, I know that this is proper because when I look at the degree of my function for the numerator, my degree is 1, because that's the highest exponential term that I have there. So I have a first degree polynomial, and here I have a second degree polynomial. So this is a rational function. My degree of the numerator is less than the denominator. So what happens here is that we are not worrying about what's happening at the very towards the origin of this function. What we care about is what's happening as x becomes unbound. That means as we take it into infinity, or positive infinity, negative infinity, what's happening there. And what happens is that as we choose numbers that are greater, greater, and greater, these other terms don't matter as much, okay? Because they're not growing as fast as our leading terms for both the numerator and denominator. So this is kind of simplified into the leading terms. So in my numerator, I just have my x, and for my denominator, I have 4 over x squared. So what happens here? If I look at just this, my leading terms, the ones that start to take over everything that's happening, well, I can simplify that, right? I can simplify this into 1 over 4x. And look at what happens here. As I keep making my x's greater and greater, what happens to all of this? Okay, my denominator, okay, gets bigger and bigger and bigger, but my numerator does not. So this ends up making my fraction smaller and smaller and smaller. So as it becomes small and small and smaller, this will always head towards 0. Okay, so this is the great thing about having a proper rational function. All of their horizontal asymptotes are at y equals 0, because this is what's always going to happen with them. Notice that even if I change this around a little bit, right? What if I chose, I don't know, I'm just going to make one up on the spot. Let's say, I don't know, 3x to the third minus 2x over, I don't know, 5x to the fifth minus 3. Okay, so I know that this is a proper rational function because my leading term is to the third power and my leading term for the denominator is to the fifth power, so it's smaller, greater, right? So the only ones that I care to look at, because those are the ones that take over, that they change the greatest, are my leading terms. So in this case, it's 3x to the third over 5x to the fifth. So what happens here? Let me just simplify this. It's still 3 over 5, and this is, oh, those are all gone. I just have x squared below. So same thing, 3 over 5, but here I'm multiplying my denominator by bigger and bigger numbers, which makes my whole fraction smaller, smaller, and smaller, and it'll always head towards 0. So once again, even here, I have that my horizontal asymptote is y equals 0. So that's a great part about these proper rational functions. Always have a horizontal asymptote at y equals 0. All right, now what about this scenario where I have an improper rational function, but the degree of my numerator is the same as the degree for my denominator? So in this case, I'm looking at my leading terms, and I have 8x squared over 4x squared. So those are the ones with my terms with the highest degree. So those are the ones that I'm going to look at, okay, as I did before. So look at what happens here. I care about my leading term, so I'll pull that out. So 8x squared over 4x squared. Now this time when I simplify this though, I get 8 over 4, which is the same as 2. I didn't have any x's there left over and had to see what was happening as I increase the x's, as I approached infinity or anything. I get a number. So this lets me know that this will approach positive 2. So all I really need to look at is my leading terms to see what's happening there. These are good to work with as well, because you'll get your horizontal asymptotes right away. Okay, so here I have another scenario of an improper rational function where the degree of my numerator is greater than the degree of my denominator by 1. Now that part is really important. What we're about to look at here is when my degree is only up by 1. Okay, we'll have a different scenario if it's greater than that. So when I look here, my leading term has an exponent of 4, and this one has an exponent of 3. So I'm good. It's up by 1. So what you're going to do here is some long division. Okay, so I'll do these steps slowly in case you haven't seen it before, or you're taking your notes with this. Okay, so what I'll do here is just like you've done long division before. If you had been asked to do, I don't know, 10, let's do what's longer, 100 divided by 2, and I used long division for that. Okay, we're taking the same steps. 2 goes into 1 0 times, 2 goes into 10 5 times, so times 10, and I subtract, and I keep going, right? I subtract that, bring down my next place value. In this case it's 0, 2 goes into 0 0 times, so my answer is 50. I don't keep going because I don't have any remainders. If I had a remainder, then you write out what you have left. So we're going to do those same steps, but for this crazy thing, right? So let's take a look at what that looks like. So I'm going to write x to the third minus x squared. I like leaving a space, plus 1. Why did I leave a space? Because there's nothing here. I like to write them in descending degrees. Okay, and that gets to, I'm going to write 3x to the fourth. There's nothing to the third, so I'm going to leave a space, minus x squared. So I left my space there. It's what I'm used to. So let's see. I'm going to look at the first term. I have 3x to the fourth. Remember, I need to make them the same, right? This doesn't have a coefficient, so I need to multiply this by 3. And I need to make it x to the fourth. So I need to also multiply this by x. If I do that, when I multiply 3x times this, I'm distributing now. Okay, so 3x times this gives me, let me use different colors so you can see it's different. This gives me 3x to the fourth. Now if I distribute it here, I have to do it for the rest of them, right? So this gives me minus 3x to the third. So that would go in this spot. That's why I left it blank. Minus 3x to the third. Okay, there's no to the first power here. Now I multiply it by this and I get plus 3x. So 1 times this gives me plus 3x. And I'm going to write it here, plus 3x, because we need the place values to match. Now, the next part of my long division was to subtract, right? Now, you need to be careful here because, when we do the regular long division, we just write minus and we just subtract. You can't just do that here because this is a whole polynomial. So if I write minus here, what you're actually doing is subtracting all of these terms. So what has to happen is, this is what's actually happening. You're saying minus all of this. Now this should look familiar because you need to really distribute that minus to all of those terms there. So this is actually minus 3x to the fourth, like you've seen before. And instead of minus 3x to the third, this is plus 3x to the third. Instead of plus 3x, it's minus 3x. Okay? So once I distribute that out, this is actually what I have and what I'll add together so that I can subtract properly. So here, this is canceled out. Here, there's nothing to do, so I'll just bring it down. Plus 3x to the third nothing to do, minus x squared, nothing to do, minus 3x. Whew, okay. So I can keep going though. So I can do one more division because look at my powers. I have x to the third and x to the third. I can do something about it. So in this case, I'm going to, well, I noticed the only difference they have is that this has a coefficient of 3. So I need to multiply this by a positive 3. When I do that, I get plus 3x to the third. Remember, I got to do to all of them. So now it's minus 3x squared plus 3. Okay, so I'll simplify this one more time. So this is gone. Oh, sorry. What did I forget to do? Switch all my signs. So minus, plus, minus. Okay, now it's gone. And here I get 2x squared, right? So minus x squared plus 3x squared. So I get 2x squared minus 3x and minus 3. So this is my remainder. I know this is my remainder because I can't keep going because this is x to the third power and this is x to the second power. I can't multiply it by something to make it less. So that's where I stay. So this is why you did all of this work. Here, this is a asymptote, but that looks like a line. And you're right, this is a line. It's not a horizontal asymptote. What's happening here is that you have an oblique asymptote. You have an asymptote that's slanted, okay, that's oblique. So here my asymptote is actually at y equals, and you write down what you got here, 3x plus 3. Okay, so this is the asymptote that you have here. You have to do it by long division. You'll see videos where they tell you, oh, only worry about the leading coefficients, just like you're doing before. And if you do that, you're going to miss, though, you're going to miss the y-intercepts for your asymptotes, for your oblique asymptotes. So be careful with that. Okay, what about our last scenario where we can have an improper rational function, and yes, our degree is greater than what for our numerator than what we have in the denominator, but it's greater than 1. In this case, we have a 5th degree polynomial over a 3rd degree polynomial, so it is greater by 2. Well, what happens here in this case is that there is an asymptote, but here in college algebra, you most likely will not find it because they're only interested for you guys for the just horizontal and oblique asymptotes and vertical. This is actually approaching a quadratic asymptote. So right here, we would just say that there's no oblique asymptote or horizontal asymptote. And I'll just show you quickly, the only reason I know that it reaches a quadratic asymptote is, and I'm going to take a shortcut, even though I should use long division for this, just so you can see really quick, since we're not really going to work with this one anyways. If I take my leading terms, x to the third, and I simplify that, I get 3x to x squared, 3x squared. So if I graph this, it would approach something close to this, 3x squared. Remember, I'm missing something here because I didn't do long division. But notice that it's not linear. Okay, so I don't have an oblique asymptote. I have something that looks more quadratic. So usually in this stage, you don't find those. So for right now, just say no horizontal or oblique asymptotes. Go ahead and try these 5 problems out where you're finding the horizontal or oblique asymptotes of everything we've just learned. And I'll show you the answers in 3, 2, 1. All right, here are your answers and work. So let's break it down. For your first one, Well, that's a good one to have, right? Because the degrees are the same, I just have to grab those leading terms. I see that it ends up simplifying to 3 over 1. So my horizontal asymptote is at y equals 3. For my second one, great. There's no work involved because my degree of my leading term for the numerator is greater than 1, right? It's 4, and this one is at 2, greater than 1, so I don't have to do any work. I just say no horizontal or oblique asymptotes. Number 3, also a good one to have because it's a proper rational function, so there my horizontal asymptote is always at y equals 0. Number 4, though, here it is improper, but it's only higher by 1 degree, so I have to use my long division. So here's my work for the long division. Hopefully it looks the same as yours, and I end up getting that my oblique asymptote in this case is just 3x. So y equals 3x is my answer here. Now, number 5, there are some things that might have thrown you off. First, your leading term is actually not all the way in the front. It is the second term for my denominator, and I see that it's 3 and 2. So there I have to use my long division again. So using long division, something you have to be careful here with is that I like to, remember, you're writing them in descending power order, and here my coefficient for my x squared is -1. Okay, that negative stays with it. So if you switch the order, okay, it should look like this, -x squared plus x. That's what my denominator is. So here the very first thing I had to multiply by was my -x. Multiplying by -x gives me the terms I need, and then I switch the signs so that I can add them together and start my simplification process. So here's the work. Hopefully you did well. If you didn't, try it out again so that your work matches mine. Okay, so that's where we'll end it for this lesson. If you want to stick around, I'm actually going to show some of these things, how they work in Desmo, so you can get a visual as to what's happening here with the asymptotes. Okay, but if you're done, then hey, you got it. So if that's the case, until next time. Okay, so if you're still here, it's because you want to see visually what was happening with all these asymptotes, talking about the graphs that will get close to them but never reach. So let's take a look at the problems that we looked at, right? So for number 1, this is our graph, okay, 3x over x plus 4. So here, okay, zooming out, we can see what that starts to look like, right? And it looks like it's reaching something, but we don't know what it was until we solved for the asymptote. In this case, was y equals 3. And we can see as we zoom out that that is the line that our graph will approach, but never cross. Okay, remember that your asymptotes deal with as x becomes greater, as it approaches infinity and negative infinity. Okay, our next one, we said that there was no asymptote, horizontal or oblique, and let's look at that one. Well, here we have what looks like a quadratic, right? So very similar to our quadratic. So there we don't have any asymptotes that it will reach towards. For our next one, number 3, this was our graph, and we said that, hey, our horizontal asymptote here was y equals 0. Y equals 0 is our x-axis, but here we notice something weird. It crosses it, doesn't it? Well, remember that for asymptotes, what we care about is what's happening as we approach infinity. So zooming out, we get a better look of what's happening there. So your asymptote might get crossed at some point, but as the numbers get greater, then that's not the case anymore. Okay? For our next one, we said that we had an asymptote at 3x. So this is what our normal graph looks like. And if we graph 3x, once again, you see that there's an intersection here, but the more we zoom out, we see that, hey, it really is an asymptote as the same way that you're used to looking at it. Okay, that the graph will approach it, but not cross it. So here we see what's happening there. We have to zoom in quite a lot in that case. Okay, and then for our last one, here is the graph of our last one, and we had an oblique asymptote. Okay, looks really nice with this one as it's approaching it but not crossing it in both directions. Okay, so there you go. You have your visual for what's happening with your asymptotes. And as I say in every lesson, just keep practicing, and you'll be good. Okay, until next time.